Hello, my name is Jan, and I am an assistant professor at the Department of Nutrition, Exercise and Sport at the University of Copenhagen. In this video, I will give you an introduction to pre-processing of LCMS data. I will explain what the goal is, what some of the challenges are, and give some detail on how it is practically done using the R package XCMS, that is one of the most used tools for pre-processing of LCMS data. Before we start discussing how preprocessing works, let's first consider where in the metabolomics pipeline it takes place. In a typical metabolomics study, we have collected some samples, maybe from a meal study where people have gotten different things to eat. We have then collected samples, could be urine samples, blood samples, or feces samples, and we have analyzed these samples on an LCMS instrument. We then end up with three-dimensional data because we have retention time, mass, and intensity, and even multiple samples. Before we can perform statistical analysis, though, we need a normal table that have the samples in the rows and features that represent compounds in the columns. And this step going from three-dimensional data to a normal table is what we call pre-processing. The goal of this video will be to explain how we go from the raw LCMS data to a two-dimensional table that we can use for statistical analysis. To do this, we need to understand what is the data structure of this LCMS data. We need to locate and integrate peaks. This is what we call peak picking. When we have done that in all the samples, one sample at a time, we then need to align the peaks across samples, meaning we need to figure out which peak in sample A is actually the same peak in sample B. Then we have the problem that in LCMS data, we typically see a decrease of intensity as we analyze more samples. Correcting these artifacts is called batch correction. Before we look at the data structure of LCMS data, let's first remind ourselves how the data is created. When you inject your solution in the chromatograph, all the compounds are mixed together in the solution you are injecting. As the compounds pass through the chromatographic column, they are separated. The reason they are separated is that compounds that stick to the column take longer to pass through the column than compounds that do not stick as much to the column. In this example, you see that the red compound passes quickly through the column, whereas the blue compound sticks more to the column and therefore takes longer to pass through the column. So the red compound exits the column first, and we can detect it separately from the blue compound that arrives to the detector later. Now let's look at what happens after the compounds exit the chromatographic column. When the compounds exit the chromatographic column, they exit in a spray and they are ionized. In the most typical setup for LCMS metabolomics, electrospray ionization is used. Many of the compounds are ionized in their complete form, but some of the molecules also break up into smaller pieces. We call this in-source fragmentation. In the quadrupole and collision cell, nothing of interest happens in the profiling experiment. Then the compounds reach the time-of-flight tube where they pass through an electric field, and compounds with a low mass pass faster through the time-of-flight tube. So just like in the LC, we can then detect the different ions separately. There can be multiple ions that correspond to the same compound because of the in-source fragmentation, but also because of adducts. We will explain adducts more in detail later, but it means that instead of just ionizing by removing or adding a proton, some compounds can also ionize together with other atoms. Typical atoms is sodium, potassium, and chloride. Since they have a different mass than hydrogen, you will see also multiple peaks in your mass spectrum. So now we will look at what this means in terms of data structure. Here's a representation of a single sample of XCMS data where we have zoomed into a small area of the data. We have retention time on one axis and the mass to charge ratio on another axis. We are only looking at 4 mass spectra here. They are shown in different colors. So at a single point in time, a mass spectra is recorded. After a short interval, the next mass spectra is recorded. We thus have 3 dimensions: retention time, mass, and intensity, and that is for each sample. When we talk about peaks in LCMS data, we can mean one of two things: a mass peak, that is, a peak in the mass spectrum, or we can mean a chromatographic peak. That means a peak in retention time dimension. So where do these chromatographic peaks come from? They appear because the compounds do not elute instantly from the column. The compounds elute gradually. If, for example, we again look at a small section of our data and follow the green peak, we can see that the compound started eluting, the intensity increased, and then decreased again. A chromatographic peak is constructed by joining the same mass between consecutive scans. They will typically have a near Gaussian shape, but you can also see tailing. In this example, all the peaks have a pronounced tail. The areas under these peaks are what we are interested in, as the area is proportional to the concentration of the compound. It is, however, important to note that you cannot compare peak areas between different compounds and conclude anything about their relative concentrations. The so-called response factor is different for each compound and is mostly related to how easily the compound ionizes. Now we zoom out and look at a complete sample from above. We again have retention time dimension, a mass to charge dimension, and the intensity is in the upwards dimension. Here you can clearly see the chromatographic peaks. As I mentioned in the previous slide, what we would like is the area under each of these peaks. These chromatographic peaks for a single mass is also what we refer to as features. The peaks you can appreciate in this plot is in reality only the largest peaks. There will be many more smaller peaks that you would need to zoom into to visualize. Typically, there are thousands of peaks in each sample, depending on what kind of sample you are working with. What you also need to remember is that multiple peaks, or features, can originate from the same compound. That is because of the fragmentation and adduct formation mentioned earlier. For example, in this plot, I have marked 3 peaks that appear at the same retention time. Since they appear at the same retention time, it is plausible that they originate from the same compound, and we thus have 3 features that represent the same thing. So now we get to the part where we need to quantify these peaks, meaning we need to calculate the area under all those peaks. How hard can it be? Calculating the area under a line is easy, so what is it really that makes this difficult? Well, let's look at some of the challenges that makes it not so easy. First, we need to determine where there really is a peak and where there is just noise. We need to decide where the peak starts and ends. We could have overlapping peaks. What do we do with those? And we also have the problem that the measured mass to charge ratio is not exactly the same in each scan. So we need to decide which mass peaks are actually coming from the same compound. Take a look at this small section of data for a single mass. This is a terrible situation. How many peaks are there? It's very difficult to tell, and it probably depends on how willing you are to risk also including peaks that are really just noise. 4, 5, 6 peaks at least can be counted by eye. But how do we make a computer find them? Let's start with a simple example where we have only a single peak. Our first problem is that we don't know which mass all the peaks are supposed to have. So we kind of need to cut the data up blindly. At least that's what this so-called match filter algorithm is doing, which was the first that was developed for XCMS. We will use that algorithm as the most simple example to start with. So here you can see that we have cut two slices of data, one going from 268.05 to 168.15, another one with higher masses from 268.15 to 268.15. You will see that it looks like our real peak actually falls right between these two so-called bins. Some of the data points have ended up in the upper bin here, some of them have ended up in the lower bin. So what the algorithm does is it combines adjoining bins, so we get one bin where we have a nice peak. We cannot, of course, at this point know that there is a peak, so how do we find a peak? Well, the way that matched filter does it is by using a so-called model peak. So we take a Gaussian-shaped peak, we, so to speak, pass it along the data, and when the model peak correlates well with the data, then it means there must be something peak-like in our data. That is what we have seen here. In reality, we are not using a Gaussian and passing it along the data. What is actually compared to the data is the so-called second derivative of a Gaussian peak. You will also see that referred to as a Mexican hat because of the shape. The Mexican hat also have the nice property that where it crosses the x-axis is a reasonable estimate of the end and start of a peak. So using this, we can define where the peak starts and ends, and we can calculate the area under this peak. The problem with the approach I just showed you is that the model peak has a certain width that you need to choose. But in reality, not all peaks have the same width. In this example, you can see that the chosen model peak is clearly too wide. So what can we do? Well, we could make the model peak smaller. That seems a bit better. Or what about even smaller? We might have gotten some noise included here, but we could probably live with that. So we just use a small peak width on our model peak, right? Let's see what happens if we try that at another point in the data. Ooh, that's very bad. So this clearly cannot work on all our data. We simply cannot find a good peak width that nicely covers everything. This is one of the problems the newer, so-called send-wave algorithm tries to solve. So what it does instead is that it tries on hats of all sizes, so to speak. Meaning that for each peak, it tries to figure out what the ideal peak width is. In this example, it looks like it has decided that all the peaks have the same width, but that is of course not always the case. So happy with this, we can move on to another problem the send-wave algorithm has tried to solve. And that is the problem of binning. Remember that we cut the data into mass slices to get chromatograms? That is called binning because we create bins of mass intervals. The problem with that is that if we are unlucky, we end up just like in the example where a peak was cut in pieces because some of the measured masses fell into one bin and other fell into another bin. We did the trick of combining bins to safeguard against that, but that means that we practically end up with very wide bins, much wider than the resolution of our mass instrument. So we are effectively throwing away accuracy, and we could end up combining things that do not belong together and that our instrument is perfectly capable of separating. Okay, so what can we do about it? What they did with the send-wave algorithm is that they avoid predefining bins completely. Instead, it looked for regions that looked like they could contain a peak. The way it does this is by using the observation that when the intensity of a mass peak rises above noise level, the measured mass becomes more precise. So noise is more random than where a mass is measured. So for there to be any chance of a real peak existing, it says that there must be at least X consecutive peaks, mass peaks, where the mass deviation between them is not more than Y. That is what we see in the box here, and the intensity is shown by the colors. So we can see that when the peak becomes intense, the mass is stable, and we can say that there could be a peak here. These regions are called regions of interest. We then have to do the things we just discussed to figure out exactly if there is a peak and what shape and size it has. Here we have zoomed out to a larger section of the data, and we can see that it has found certain sections that look like they could contain a peak. Also note that most real data always falls in bands with approximately 1 unit mass between them. That is not by chance, but because the mass of all atoms are close to a whole number, and therefore the mass of a molecule will also be close to a whole number. If what I have explained so far did not sound difficult enough, our problems have just started. Because at this point, we have found the peaks in all the samples, but we don't know which peaks found in the different samples are actually the same peak or compound. So we need to match all the peaks between samples. So here our problem is that retention time can shift a little bit between samples, and the mass won't be exactly the same in all samples either. So we somehow need to match the peaks across samples while allowing for this variation. It can be difficult because we don't want to declare that two peaks are the same across samples if they just happen to be closely eluding and have approximately the same mass. So a compromise needs to be found between merging things that are not the same and not realizing that two peaks in two different samples are the same just because their mass and retention time vary slightly. So let's look at how XCMS handles it. This plot might be a bit confusing, but on the x-axis you have the retention time, and each dot with a line is a peak found in some sample. We don't know which one, and it doesn't matter for this purpose. Also note that we are looking at a small mass range, so all the peaks here have a similar mass. The idea is then that where there are many peaks found, it is probably because these are real peaks that are found in many of our samples. The way that we figure if there are enough peaks in a certain area and who belongs together is by calculating the density of the peaks. It can be difficult conceptually if you're not used to this kind of method, but the idea again is that if there are many peaks, the density is high, and we can then declare that there are real peaks consistently in that retention time range. Here again, we need to make a decision. When we calculate the density, we need to define the so-called bandwidth in our density function. A low bandwidth and we get narrow density peaks that encompass a small retention time range, and a higher bandwidth and we get broader density peaks that encompass a larger retention time range. If the bandwidth is too large, we might inadvertently combine peaks that are in reality different. And if the bandwidth is too narrow, we might end up with two features in our feature table for the same compound. So we are done. We now know which peaks are the same in the different samples, so we can construct a peak table like we wanted. Each feature in the columns and a row for each sample. Done. Or perhaps we can do a little bit better. Because you remember I explained that the retention time of compounds can move a bit between samples. We could try to fix this before we collect the peaks across samples. In the example here, you can see that some of the peaks are misaligned. So we could move each sample a bit so that they line up better. if you use the so-called OB-WARP algorithm in XCMS, this is more or less what it does. It pulls and stretches the raw data to align better. This is very slow though, so not what I would recommend doing. So let's instead look at what the standard algorithm in XCMS does. Again, I have one of those plots that seem very unintuitive when you have not seen it before. So let me explain. On the x-axis, you have again retention time. Each line is a sample and each dot is a peak we found the first time we matched peaks across samples. On the y-axis, we then have how much the samples need to be moved to have the same retention time as an average sample. So for each retention time, for each sample, we can now know how much we should correct the retention time. So now we can go back to the peaks we found in each sample, adjust the retention time, and then try to match the peaks across samples again. This time it should be easier to match them, and we can use a more narrow bandwidth and avoid merging peaks that are just close in retention time, but really are different compounds. Did you think it was that easy? No. Also here we need to decide on one parameter. For the line we have drawn through the peaks found in each sample, we need to decide how smooth or flexible we need to allow that line to be. Here a span of 0.01 is definitely too low. 0.2 is not too bad, but here it seems like it is overfitting. So 0.6 would be my choice. If we make it too flexible, we will overfit and likely not make the data better. If we make it too smooth, we won't be correcting the retention time enough, and it won't help that much. So what I look for when deciding on the span parameter is the lines do not go up and down all the time. It is simply not plausible that at one retention time, compounds were eluting later than the average, then a bit later, the compounds started to eluting earlier, and then suddenly they were again eluting late. It can change direction across the run, but not up and down all the time. So I'm looking for a curve that doesn't change direction all the time, but is not smoother than it needs to be. There is one last thing we need to do before we can declare our pre-processing finished and move on to exploring the data. When we do peak picking, there will always be some peaks that are not found in all the samples. So we need to decide what number we want in our peak table in this case, because having a table with a lot of zeros is bound to give a lot of problems when we need to do the statistical analysis. Let's first consider why peaks would be missing. It could be that a certain compound simply is not present in a sample. That is of course okay. But it could also be that it was not detected well due to ion suppression, which means that other compounds or buildup of material in the instrument prevented the compound from being detected. It could also be because the chromatography for that compound was not very good, so you got a strange peak shape that the algorithm is not picking up consistently. It could also be because your peak picking or grouping parameters were not optimal. So what can we do to quantify what is in the data that we didn't pick up? Well, we know where the peak is supposed to be. The other samples told us. So what we do is look for a peak with that mass at that retention time, and we simply integrate what is there and don't bother with peak shape or if it is a very small, bad-looking peak. We could of course be picking up some noise, but that is often a better result than missing peaks that are there or leaving zeros in our table. So what I will explain now is not really pre-processing, but it is useful to discuss here because we practically perform this analysis right after pre-processing and before statistics. The issue we want to solve now is the issue I mentioned in the beginning with multiple peaks originating from one compound. It means that our peak table will have multiple features for some compounds. That is something that is very nice to know when we do statistics. Are there 100 or 10 compounds that are different between those two sets of samples that we are investigating? That would be nice to know. So again, let's look at the example from earlier. How can we figure out if these peaks just have the same retention time or if they are in fact coming from the same compound? Well, we could use this beautiful data that we just collected because there are a couple of things we know about features that come from the same compound. First, they need to have the same retention time, but they also need to correlate across the data. That means that if a sample is present at a higher concentration in a sample, all the features originating from that compound will have a higher intensity, and vice versa for compounds with a low concentration. Ignore the colors in this plot, but here each dot is a sample, and on the axis you have the intensity of two features that come from the same compound. You can see that they are highly correlated. So we can use this to figure out if any two features could be related. To check if two features are really co-eluding, we can also look at the raw data more closely. If they are closely eluding, the peaks will overlap. But to compute if they are overlapping, we take the intensity at each scan and plot against each other. Again, if they are co-eluding, this data will correlate. We then combine these correlations into a score. We then combine these correlation coefficients into a score, build a network with things that correlate, connected, and we can then see which features belong together. So if we take a look at our peak table, here we have flipped it around so each row is a feature defined by its mass and retention time. Ignore what I've grayed out for now. The R package that will perform the analysis I just explained is called camera, and the output will look something like this. You see in the last column that it has added a number. The number itself doesn't mean anything, but features that have the same number is thought to come from the same compound. So we now know who belongs together. But we would also like to know what the relationship between the features are, and camera can also help with that. If we look at the isotopes column, it says that these two features come from the same isotope cluster. This is the normal peak, and this is the +1 isotope. Same for the two other groups here. Then it also tells us that it thinks that this is the pseudomolecular ion. That means that is the one ionized by adding a proton. And this is the sodium adduct. And here we have a number of fragments. So in this case, the annotation is perfect. But this is rarely the case, and you should only use these annotations as a rough guide for you to understand what the compound is. Hello. Yes, I'm still here. You have now created a peak table, but you should be wondering, is it any good? How do I know if I did well? We will look at some of the ways to check the quality of the data. But first, let's look at why it is so difficult to know if untargeted metabolomics data is good. First, we are measuring both known and unknowns. So we cannot, for example, have internal standards for all the compounds that would allow us to know if each compound is recorded reliably. Even if we somehow had the capacity to buy thousands of standards, they are simply not available to buy. We also have the problem of each metabolite giving rise to multiple peaks. So which one are we supposed to look at? Finally, it can be difficult to distinguish actual metabolites from contaminants. Okay, before we get to what we can do about it, let's go back to the beginning, before you analyzed anything in the lab, and set you up for success. First, if you do nothing else right in this world, make sure that you always randomize your samples. Otherwise, you will never be able to know if what you see in your data is the truth or just an effect of the order in which you analyzed your samples. Next, inject blanks to check for carryover and contaminants. You can use internal standards that can be somewhat helpful to understand the quality of your data, as well as maybe do something about it afterwards. But even more important is that you also inject so-called QC samples. They should be injected regularly during the analysis of the samples. By QC samples, I here mean ideally a pool of all the samples in the study, or it could be a reference sample that you use in all your studies. So now you have recorded the data, you're sitting in front of the computer. What should you do? Well, you should know your samples a little bit. By that I mean you should have some compounds that you know should be there. So you can go check now in your peak table, are the compounds that I know should be there actually found? And are they represented in a single feature, or are they split between multiple features? Do you see all the expected fragments and adducts grouped together? For example, in biological samples, my best friend is tryptophan because he's found everywhere and he cannot really be mistaken for anything else. So I can check, is tryptophan found in my peak table? Does it have all the fragments and adducts that I know should be there? And is there only one feature that represents the pseudomolecular ion of tryptophan, for example? Now that you have checked if the peaks that should be in your samples have actually been found, you trust that the peak picking was done okay. The next thing you can do is use the blank samples to remove features that are not related to your samples. That would be features coming from solvents and contaminants and buildup in the instrument, for example. The way you can find those would, for example, be to say, give me all the features that are found in just as high amount in the blanks as in the rest of your samples. Those are probably irrelevant. The next thing you can do is try to remove features that we cannot record reliably. A typical way of doing this is, for example, to take your QC samples that should all be the same and look at the coefficient of variance. People often use 30% as a cutoff. So if the coefficient of variance is higher than 30% in the QC samples, the feature is discarded. This is not the best way though, because you could have features that are very difficult to detect, but there could still be some useful information there. So a better alternative is the so-called D ratio. And what the D ratio is it's the standard deviation of the QC samples divided by the standard deviation of the samples. If the D ratio is high, it means that the variation in the QC samples is just as high as it is in the samples. That means there cannot be any useful information in the samples if they vary to the same degree as the QC samples. If there was any biological information, the variation between the samples would be higher than in the QC samples. The last thing you can do is use the QC samples to model and correct systematic drift, and we will look at that next. Now that we have collected the data as well as we could, let's look at what the data can look like when you start digging into the pre-processed data. Here are some examples. So let's say that a single compound in the first batch looks like this. Each dot is a sample. The red dots are our QC samples, and on the x-axis is the order the samples were analyzed in, and on the y-axis the intensity of that one feature. All looks nice. The QCs have the same intensity more or less, and you have some random biological variation in the samples from the study. But the next batch of samples you analyzed a day later looks like this. All the intensities are now lower. This can happen because the ionization efficiency for some reason got lower. It could be a solvent with more contaminants, or just buildup of material in the instrument that is causing this. So not so good. We will get back to what we can do about this, but just a few more examples first. You could also see a situation like this, where now the intensity is dropping within the batch. We call this intra-batch drift, whereas between the first two batches, we only had inter-batch drift. So we see a linear drop in intensity as we analyze more samples. But it could be even worse and look like this. So now we have a nonlinear drop. So now the question is, what can we do to fix this? For the first two batches, we could normalize the mean of the batches using the QCs. So we divide each batch with the mean of its own QCs. We then multiply with the global mean to get similar intensities as before. That would work well when you only have inter-batch drift. But it doesn't solve our issue when we have intra-batch drift, not when it is a linear, nor when the drop is non-linear. So what can we then do? What we could do is fit a linear curve to the QCs. For each sample, we then use this curve to correct the signal. Here it is shown where we subtract the fitted model values, so where the line is, from the signal, and then add the global mean. It could also be done using division and multiplication instead. But in this way, we can fix a linear drop. But as you can see, it doesn't do well when the drop is nonlinear. For that, we could, for example, use lowest regression. You can read elsewhere about what lowest is, but for our purpose, it is one of many ways to fit a curve through data points. So we fit a lowest curve through our QCs and use that for correction. Here I have just fitted one lowest model across all batches. As you can see, that doesn't work well since we have these big jumps in the intensity that the lowest regression cannot model well. So what we should do instead is make one lowest model for each batch to fix the intra-batch drift, and then we correct the mean between batches afterwards, like in the first example I showed you. Now that you believe your data is good, we do one final check. You perform a principal component analysis or something similar. The most simple check you do is look at where the QC samples end up. If you have done well, you should see the QC samples close to the middle and close to each other. With the drift correction method I have just shown you, you should be a bit skeptical still. Since we use the QCs to fit our correction model, they will always be close together. You should also check that your batches are randomly distributed and that there are no trends related to the analysis order in your PCA plot. If all that checks out, you should now be able to move forward to your data analysis.